Okay, Al. So today our goal is to kind of understand tangent planes. Now, our goals as written here, finding a tangent plane, find a local linearization, find a total differential. These are actually all the same thing. I know they sound scary. They're very, very slightly different. We're going to start just on the whiteboard here. Let's think up what we would mean by a tangent plane. Actually, let me start with what I would think about as a local linearization, but I'm going to start with that in kind of a dumb way. I'm going to say, all right, over here I've got my usual, right? So I've got an X, I've got a Y, I've got a Z. Someplace down in here, I've got a value A comma B, right? That's a point A, B. Up here above that somewhere, there's some kind of surfacey stuff going on, right? And there's some value that's up here associated to that surface, right? So that's, I'll take a second. Think about what that is. Ought to be, oops. Oh, good. You get a second while I screw around drawing. That's going to be the point A comma B comma, yeah, f at A and B. There's nothing else for it. It's on the graph. So I know the Z value is the output there. Okay, so let's say that I wasn't totally sure how to evaluate my function f at a point somewhere else, right? So like say close by over here, I had some other value and I was worried because I can't quite figure out what this height ought to be. So here's how I might start by guessing that, right? So my thought process is I'm gonna look at f of x and y, and I'm gonna pretend that I only know things about my point at A and B here, right? So I'm gonna say f of x and y ought to be about. So first pass, dumbest guess, that thing's flat, right? It's a dumb guess, but it's a guess, right? So I'm going to say f of x and y is f at A and B. That's a shitty guess, but whatever. You know, this is like, just assume the function's always 2. Like, sure. So this is me guessing like a horizontal plane. This is me guessing a constant. I'm going to add some information to this. So I'm going to say, well, what if I knew about, oh, and I was using red and blue for these earlier. So what if I knew about this slice and I had a tangent vector there? So what if I knew that I could add some information? Well, I could take the slope at AB in the x direction. So remember, this is the x direction slope. And then I could multiply it by, well, I've got to multiply it by a run, right? And remember this fx, I want you to think about that as the change in f per change in x, right? So that's like delta z over delta x. It's really like a df dx, right? Except this has too many variables, so it's like a partial with respect to x of f. But I should have to multiply this by some kind of a like dx. So I'm going to multiply this by x minus a. That's literally just how far did you have to go in the x direction to get to this point, my new pink point, right? So do I think that's about right? Well, not really. It's probably it's sloped in the other direction too. So that's where I'm like, okay, so I'm also going to put in my red slice here, right? And I'm going to say it's that far in the red direction, right? So I'm going to add to this fy at A and B, but now I need to multiply by a run, right? So this is like a change in f per change in y. So I need to multiply by a y run. So how far is it in the y? Well, it's y minus b, right? So this is me saying, look, the value at x and y ought to be about where you start plus any change due to x's times how far you went in the x plus the change in the y due to how far you went in the y. Like, that's it. There's nothing else here. Cool thing is, this is a local linearization. Right, that's kind of neat. Gives me a way to approximate. You actually use these all the time. You're pretty used to doing something like this. This is actually kind of how your calculator gets answers. Your calculator does something a little bit more robust. It's not quite local linearization. It's like local polynomialization, which we're going to get to in a second. So that's local linearization. A tangent plane is one that's not really actually different at all. A tangent plane, I just do this. I say the tangent plane as a function of x and y is actually equal to f at AB plus fx at AB times x minus a plus fy at AB times y minus b. Like, that's actually just equal. That's all this is. So this is the tangent plane to the function f at the point AB is given by this formula. So the kind of parenthetical is tangent plane to function f at point AB, right? And then a total differential is actually just me rephrasing my linearization. So I'm going to say that change in, say, f is basically the change in f due to change in x times x change plus change in f due to changes in y times y change. Like, this is the start of a linearization. Linearization is, or the differential is just you saying, okay, so these are the changes, but if I talk about instantaneous movement, right, I'm going to say df is partial of f with respect to x times dx plus partial of f with respect to y times dy. You guys actually use these some. Remember when you do u substitution in one-dimensional calculus? This is the total differential. So the thing I want you to recall kind of off to the side here is, remember when you do something like, let's say u is 2x plus 4, then you say du is 2 dx. Right? You guys use these some. This total differential thing just gets a tiny bit of use. We actually use it pretty heavily in differential equations. I'm going to have you calculate them in here, and then we're going to call back to this in DEs. So this might be a good thing to put in your head. But it should live right next to linearization, should live right next to tangent plane. There's one more kind of bonus thing I want to add to this, so I'm going to add a bonus thing here. So I'm gonna have to move some stuff around, aren't I? Oops. Let's just grab all that crap and scoot it down a little bit. Oops, daisy, lost a line. Get that line with it. So the thing I want to add to this is that a local, oops, that's not very well formatted, Joe. A local linearization is actually the same thing as a first order Taylor polynomial. If we were going to get second order Taylor polynomials, it's not very hard. I'm just going to throw it in here as a bonus. So write down Taylor polynomial here. Okay, so the way we'd build a Taylor polynomial is would be like, okay, so f of x and y is given by, right? And I'm going to do 0th order Taylor polynomial is we just evaluate f at a and b, right? It's 0th order because there's no variables in it. First order is going to be we do fx at a and b times x minus a plus fy at a and b times y minus b. Okay, so that's kind of first order. So this guy here just by itself is 0th order. This whole thing is first order. Now I'm going to add to that, and the second order stuff's going to be, let's see. So what if there's changes in f due to the way it's bent? So remember, this is me just throwing a tangent plane at it, right? That's like throwing a tangent line at a function. That's not very good. We can do better. So the approach to do better is we'd add more derivatives. So I'd be like, okay, so what if it's bent in the kind of XX direction, right? I'd evaluate that at AB, then I need to multiply that by x minus a squared, right? This guy's kind of like change in f. So this is like change in f per change in x, change in x. And this guy's change in x squared. So you can see I kind of cancel that. I get change in f. And it's the stuff that's due to the way x changes and x changes, right? Really, that's kind of concavity in the x direction. Then we'd add to that. We'd add an fyy. That's going to be done at a and b. We'd multiply this one by y minus b squared. And then this is the hard bit. There's an fxy at a and b. We'd have to multiply that one by x minus a times y minus b, right? It'd get both runs. Then we'd add here an fyx at ab and multiply by x minus a times y minus b again. And remember, there's a theorem that we just learned that says I could really say, fxy and fyx are probably the same thing. So I'm just going to slap a 2 in here. French guy starts with C, rhymes with Leroux. Okay, so that's our second order. So first order was just this first bit. Second order is the first bit and also this new stuff. Third order is going to be a thing that we could do. It's going to be f triple x, f triple y times some appropriate stuff. And then we'll have all the third order partials. So those would be fxxy, fyx. Yeah, there's going to be a whole bunch of them. I'm not going to worry about that right now. I just want you to know there exists a second one, and we could make more. There's a bunch. We can do it. It's not impossible. It's just kind of tedious. So let me say, all right, we've got these things. I want to show you a picture of a tangent plane. So I'm going to pull in an animation here. This is a picture we looked at before. This is what we ended our kind of second order derivative stuff with. So let's go ahead and get a hold of some derivatives. So I'm going to make some functions. So I'm going to call this one fx. It's going to be a function of x and y. I'm going to call this one fy. It's also going to be a function of x and y. And now we just need to remember how we actually calculate these. So fx is going to be 2x times y minus y squared cosine of x. Oops. Times cosine of x. And our fy is going to be x squared. Oops. E. So x squared minus 2y sine of x. Those are my partials. So let me add some sliders here. Add some sliders. I'm going to call this one A. I'm going to call this one B. Let's see. We need a point. So I want this point to be above A comma B. So I'm going to put it at A comma B comma f of A and B. Okay, so there's my point on my graph. What's not working? Something's not working. heck's not working there? Oh, maybe it's just. Oh, it's just really flat there. Yeah, let's try it up here. Yep. So what happened there was I was on a slope 0, right? There was a level curve there, and I was real confused about why the point wasn't going up and down. But it's because the function's level there. Okay, so that's all working. Now I want to add. I'm going to add an implicit surface here. So the reason I'm adding an implicit surface is I want to show you that it's z equals this stuff. So, all right, let's see. First guess is I should do f at a and b. Okay, so you can see my very dumb tangent plane here. So we're going to turn that down. We're going to turn our opacity way down. No, I want it to be a little more opaque than that. Okay, so there's our first guess. This plane is not tangent. I hope you can see that. This is just a plane through this thing. Let's see. I want this to be just a little bit more transparent than my surface. I'm going to make my surface a little less transparent. Okay. So that blue thing's not a tangent plane yet. So I'm going to do some fixing. So I'm going to add to it, and I'm going to add fx at, oops. I'm going to add fx at a and b, and I need to multiply that by x minus a. Fn is not a function. Okay, cool. All right, so you can see that I still don't have a tangent plane, but I've matched the x slope. You can see that it's actually tangent to that line that it's on, but it's not tangent to the plane itself. So I need to match the y slope as well. So that's where we add our fy of a and b, and we need to multiply that by y minus b. And now I've actually got a tangent plane to my surface. So this thing here is my first order Taylor approximation. It's also my tangent plane. And in some ways, it's my local linearization. So kind of 3 different words, slightly different perspectives for the same thing. I got my tangent plane, and now I can scoot this around. Whoa. It does not like playing with zoom. So you can see that if I kind of scoot everything around here, still got a tangent plane. It's actually very cool. Yeah. So there we go. There's tangent planes. If we wanted to make a second order Taylor polynomial, we'd need some more information, right? I need to take second derivatives. We could do that. It's not super hard. I want to leave that open for one of you guys to make as an animation. So maybe make that animation. It's kind of cool. Doesn't take very long. You guys can do it. You just add the second order partials there, add them in here. Should be good to go. Cool. Thanks, guys.